I changed the subject a little bit. So today it's the chapter 3, I think, in the lecture notes. I will speak about perfect sampling of systems of interacting neurons, possibly even if we have an infinite number of neurons. So I'm not in a mean field frame anymore, so the techniques will be slightly different. And because it's much easier to explain it, I start in a discrete time model. So up to now we have been in continuous time. So that slightly changes the framework, but not so much. So let me explain you. So sampling from the stationary time evolution of possibly infinite systems of neurons. Okay. And I start with a first example, which is a imitation model, and that is very much inspired. Well, that's the ideas of a paper of De Santis and Mauro Piccioni, sitting there. Okay, and I would call that a discrete time linear Hawkes model. I will explain what I mean. Okay. So on discrete time, so t is evolving in z now, discrete time. And I replace the counting process then just by variables that tell us at each time t if there is a spike or not for a given neuron. And to distinguish that from the continuous time, so capital I now is the index set of neurons. It was 1, 2, 3 up to n, but now it can be anything countable. Okay, so this is countable index set of the neurons. So for each I in I write xt of I is equal to 1 if at t I is spiking. Okay, so if I spikes at time t, and 0 if it does not spike. So it's a discrete time counting process if you want to, just the indicators. Okay, and
they don't last more than
so I bin time into, say, 5 milliseconds, and per time bin, I just have one spike or nothing. Okay. And I'm not considering any questions of if I have a continuous model and I bin time, what do I lose? I mean, so it's a discrete time model, which I give you the transitions immediately. So associated to that, I also have a membrane potential as before. Maybe I get mixed up in the notations a little bit. So time is downstairs now, and the neuron index is here. Okay, and I don't note the n anymore because I'm not interested in mean field models. Okay, so the number of neurons is fixed. So Vt of I will still be the membrane potential of neuron I at time t. So t is any discrete time step, and that is given by the sum of all j, which are the presynaptic neurons. As before, we say that each neuron gives an impact wj to I. Remember, that was my initial way of writing it to neuron I. And then we just sum over all times before time t that j has emitted a spike. Okay, so that is x s j. Good. And notice that I start from minus infinity because I'm interested in constructing a stationary time evolution. So the idea is, if you have something stationary, then you just let the system start at minus infinity. And to make that well defined, of course, something that was very far away in the past does not really influence you so much at time t. So I add a leakage factor here. And it could be anything. So this is the GI function. So that is the leakage. Okay, so that means that if J spiked at time s in the past, since time s, the time elapsed is t minus s, and then GI is something that is supposed to tend to 0 as the time elapsed since the spike of J is very big. Okay? It's a GI because it's related to the neuron. Okay? It's I which is receiving something and is the property of neuron I that tells you how the impact of J decreases over time. It doesn't depend on J but on I. Of course, in the general model, we could put some GIJ. I mean, but really, I mean, in neuroscience, I think it's just a GI. Okay. So for Robertus, that would be a real infinite memory model. In my toy example, in the sequel, I take G to be a geometric distribution, which brings me back into Markovian frame, but that's not important. Okay, I just want to tell you a toy example to explain the things. So in the sequel, I suppose that GI is a geometric distribution, say, okay, for any t bigger or equal to 0. And also I take the W's just to indicate the presence or the absence of a synapse between J and I. So I take them to be 0, 1. So if it's 0, it means that J does not influence on I, and if it's 1, that means we have a synapse. Okay, and then the strength of them are all the same in this toy example. Good. And then I just suppose that the probability given the past, so the past are all the neurons and all the past events, that I spikes at the next time step is as before phi I of Vt of I, and Vt is something that I know at time t. And phi is not a weight function anymore, it's now a probability because I'm in discrete time. Okay, so it takes values in 0, 1. And linear Hawks means that phi depends in a linear way on the past. So it's rather affine than linear, so I suppose, and that is really just to, that phi I of little v is something of the following form. So nu will be the autonomous spiking activity of the neuron. So that is a fixed parameter in between 0, 1. And then I take plus 1 minus nu divided by n. So I'm in the... I said that I could be anything countable, but let's stick to the setting where we have n neurons for the moment. Okay, so then this is the number of neurons. And then I just take, I shouldn't take times x. Okay. So what does that mean? That means that at each time step, there is a probability of spiking which doesn't depend on anything else. This is the little nu here. Okay. So this is the autonomous spiking activity. And then there is something that depends on the potential. The little x is the potential variable in this way. Okay, it seems a little weird, but we have to make this a probability. And if you think a little bit, if I define the v in this way, you see that v is upper bounded by n. So I have to divide by n to get something which is a probability.
Nu can also be a new r. Nu could be new r.
Yes, of course. Yeah. That could depend on the neuron itself. Yeah. So what does it mean? That means that the probability that I spikes at the next time step is given by nu plus 1 minus nu 1 over n sum j equal 1 up to n wj to I, which just tells you does j influence me or not. And then I have the sum s equal minus infinity up to t of the gi. So in gi the p could also depend on I, whatever you want. Okay, so 1 minus p to the, and then p to the t minus s. And then I have xs of j. Okay. Good. So we have a sum of probabilities here. Okay. So we can interpret this formula in the following way. At each time step, the neuron decides to spike independently of anything else with this probability. Okay. So I spikes independently of anything else with probability mu. And if it does not do so, so if it doesn't spike autonomously, that is this, well then it chooses one of the neighbors with probability 1 over n, including I itself. It chooses a random memory S, okay, and then just copies the value of the neighbor it has chosen the time back that he has chosen. Okay, and that's why it's called an imitation model. Okay, so if it does not do so, then it chooses one of the neighbors with probability 1 over n plus a random memory, let's call it U, according to a geometric distribution having success probability 1 minus p, and copies the value of the neighbor. So let's say one of the neighbors, so say j, so j can be equal to I, and copies the value of j at time t minus u minus 1. I hope the minus 1 is something like that, provided that j indeed influences I, which is given by the W. Okay, so provided that j indeed influences I. So if we have transitions which are linear in the past, that means we have something which is a sum of terms. The idea is to interpret the sum as the realization of some randomized procedure, because here I add randomness, no? I don't only use a single uniform random variable to realize this transition. I use a certain number of random variables, choice of the autonomous update or not, choice of the neighbor, and choice of the time length that I have to look back in the past. And if you do it like that, then you get this interpretation, which leads us to an algorithm of simulating the process, just as I just suggested. Okay? Any questions up to there? Good. So I guess that is basically something that resembles very much to the paper by Emilio Mauro. You try to write your name as I should. Okay. So they call that imitation models with noise. Okay. Good. Maybe I should make a picture. So say time is going back into the past like that, and the nuance are here. Okay. So I have the n nuance positions and the time, and I want to know the position of that nuance at a given time, whatever this time is. We don't really care, okay, because it will be stationary. So as I said, the first thing to do is to decide if I update or not, independently of anything else. If I don't update independently of anything else, then I choose a neighbor and a time length, and say I depend on the position of this nuance 3 time steps before. Okay, then this one decides to update or not independently of anything else. It doesn't update independently, so it chooses also a neighbor 1 time step before, and so on, and say this one is regenerating. That means it chooses the new, and then we stop everything. Okay. Good. And if it does so, and if all the synaptic weights have been 1, the long of this trajectory, that just means that the value of the neuron at this time is equal to 1. Okay? And if one of the w's is equal to 0, that means we erase this error and it would be 0. Okay. So this gives me an algorithm that allows to associate a value to any of the neurons at any given time, and actually that is a way of simulating the unique invariant state of the system at a given time. Okay, so we'll now just do it a little bit in a more general frame, where I do not only simulate a single neuron, but a certain number of them in a finite space-time window. Okay. Can I still write here? I forgot it. Yeah. So simulate within a finite space time window. So the space-time window, I call that F. So it's a finite subset of the neuron indices, 1, 2, 3 up to n, and of the times I'm interested in. And to do that, I have to introduce random variables. So for each couple IT, so I is the neuron index, T is any time, we associate 3 random variables, which are the choice of updating independently of anything else, the neighbor, and the time we have to look back into the past. Okay, so I will take U, which is a Bernoulli random variable of parameter nu. Nu is the update parameter. It could be a new I, okay, but let's stick to the homogeneous description. I take capital I, IT, which is uniform on the neighbors. So it chooses one of the neighbors with the probability 1 over n. And I take the time I have to look back into the past, which is a geometric time 1 minus p. And I do all these choices independently for all different couples of neuron time, of neuron index and time. Okay. So they are IID in the indices IT. Okay. And then I just, so you see what I did here is actually a backward random walk that is associated, say, to IT. If this is time t and that is neuron I, what I did here is to construct a backward random walk that is exploring the past of this one until the first time that I fall onto a regeneration event, which is the one where the U's are 1. Okay. So we construct a backward random walk Sn IT n bigger or equal to 0, backward because we explore the past. At time 0 we start in IT, and this is constructed until the first time that I can stop. And I can stop due to 2 reasons. Either I regenerate or I choose a neighbor that doesn't influence me, okay. Which is in which case I can also, so until something that I will call NIT stop. Okay. Any questions up to there? No. Okay, so the definition is as follows. SIT0 is equal to IT. And then on the set where SNIT, say, is equal to JS, I do the following. So if the uniform which is associated to that couple is equal to 1, we stop. So we put n IT stop is then equal to little n, because I have constructed the random walk only for n steps. And in this case, I put x I of t equal to 1, because I stopped due to a regeneration event, and I did not choose any neighbors that don't influence me up to there. Okay. And then if QJS is equal to 0, then I put Sn plus 1 of it. Well, I'm currently in that position, and I go from that position to the neighbor that I choose, and s minus the time that I choose. Okay, so this will be ijs. Okay, this is the neighbor that I choose in this position, and then s minus t js. Okay.
N is minus the time.
N is minus the time, yeah. Clear? So I'm here in JS. I just wrote this transition here. Okay. So at that time I choose the neighbor, and the time I have to look back into the past, and that gives me this. Okay, and then we just have to decide if this one. Sorry.
Because it seems that with your first step, when you finish the going back, it's always a 1. So how can it be 0 sometime? No?
It's coming now. Okay. So if I choose to regenerate, it will be always a 1. But if I have, let me do a picture. I do something like this one is choosing this neighbor. But this neighbor does not influence this one. Okay, so say this neighbor is j, and this is I, and wj to I is equal to 0. Then this one will have the position 0. Okay? And this is what I wanted to write now. Okay? So I do one step further because I decided not to regenerate. I depend on this guy. So, and then I say, if w I js to j is equal to 0, then I stop. So then I still put nit stop equal to n, because it was sufficient to do n steps.
Yes, it should be 0.
Because
W is 0 or 1, yes.
Yes.
Why you choose 0? Because I think that M can be the number of neighborhood, but W is equal to 1.
I think I don't understand your question. So I took 0, 1 just to have a very simple random graph. Just to have a very simple graph.
The same J can have 0 with some I and non-0 with another.
Yeah.
So it's not that you can.
No, you never receive the signal from W that is equal to 0.
No, exactly.
No.
So
why choose W is equal to 0? You can choose only W is equal to 1, and then you choose X that you see in that moment, if it's 0 or
you see, it is my interpretation of this sum here. This is not a probability, it's a subprobability. So if I say that this 1 over n, sum j equal 1 up to n, this is a uniform choice of a neighbor. But actually, the neighbors don't influence me. I mean, it depends on the W's. If some of them don't influence me, that means that I choose a neighbor that I don't depend on. So I did something which was too involved somehow. So maybe you could tell me that it's not the point just to say that you have uniform distributions on the neighbors. But if I do it like, because this is a subprobability if some of the W's are 0.
I think what you want to do is equivalent to what she's doing, but then it's more complicated.
Yeah. Okay. I write it this way because we are working with Guilherme and Julien on a paper where the W's are random. Okay. They are so it would be the realization of an Erdős-Renyi random graph or whatever. And we wanted to have an algorithm that that works independently or for any realization of the W's. You know, if you want to take into account the exact structure of the 0, 1s, and you choose another randomness for the W's, you have to change the algorithm. But me also, but I mean, it's easier to write it this way. It's more flexible. Does that answer somehow to your? Okay. Good. So if I choose a neighbor that I don't depend on, I stop. And else I continue.
You stop and put X. Stop and put X I of t.
Exactly. Thank you. I wanted to write that. X I of t equals 0. Okay. And else, that means if the W is equal to 1, well, you continue. Yeah. So else, I replace n by n plus 1, and I go back. Well, I forgot to. I'm not a good writer of algorithms. Go back to A.
If the network is complete, like all the W I J are,
Yeah, then
it's one everywhere.
yeah, of course. Yeah.
But the whole process, which is complete, has zeros at one.
Well, she says that if all the W's are 1, what I'm just telling you is then the only invariant distribution of this is having all guys equal to 1. Okay?
If u is 0, it's the back option. Or
Maybe it's because of the choice of the parameters.
I think so. Of course, yeah. But
so one would be the one would correspond to the probability of choosing independently. The other factor is the probability of given that I'm going to choose independently of anything, what's the probability of certain of one?
Yeah.
That's a good question. If P is 0, this is the Walter model. The usual Walter model with a tendency toward 1.
if P is equal to 0, this is the Markovian frame, no? Because
this is a Walter model, a classical Walter model, but with external tendency.
yes.
P1 event. So if nu is 0, it's the Walter model. If nu and P are 0, it's the Walter model. So my question is, in this formulation, do you have a dual process? Probably, but
I think this is something like, no? I have the impression that is something.
But it's a strange duo because it's not. They don't take a set in a fixed. It's a set in space.
Yeah, okay, but yeah. So if P is equal to, what did you say, 0? That means that I always have
Looks like that's
at the last, this is the Markovian version. I just look at one step before and I just choose. Well, yeah. Yeah.
So it's a classical model.
Yeah.
No, in the comment of Patricia that you end up with only one, probably it also depends on the initial conditions. You're not considering that you start maybe with.
Of course, here I start from minus infinity. Yeah. And if the nu is strictly positive, that means that we have survival. Yeah. And then in this toy model, the only invariant measure would be all ones.
One. You know, the issue with the station is find a coalescence time back in the past of all this time, and then simulate
is the value of this for this time according to certain distributions.
Yeah, yeah.
But then again, I mean,
Because it's a model one dimension, it's not strict. But
No, I think you don't take the new equal. Yeah. Yeah.
in fact, this model, I think it was in the paper.
This we have to ask to Pablo. It's in your paper.
Inspiration, but
Well, the choice of the past is independent of change.
Yes.
but I think when you're looking at, again, the system has to have started with some initial condition.
Yes.
So if you start with all zeros, then you never get all.
No, because you have new. You have spontaneous bursts.
Yeah. If new is not there,
But
of
if
course.
new is zero, you have infinite measure.
Yeah. Yeah. Of course.
The question is, you have another one?
Yeah.
And the other model. So the answer is, if P is zero and mu is zero,
Then you, yeah.
and you have a dimension greater or equal to 2, you have a continuous of invariant measures.
Mhm.
In 1 and 2, you just have to. So you have a continuous real of invariant measures in dimension. You are working a finite set.
Yeah, it's finite. Yeah.
Yeah, but this continuous you cannot pick up by a perfect simulation.
Yeah.
You cannot pick it up by a perfect simulation.
You cannot.
Perfect. You cannot pick up the continuum of invariant measures through perfect simulation. Perfect simulations don't work when you have more than one.
Of course. Yeah.
Well, it depends what you mean by that, because I guess you wrote a paper with Pablo Ferrari with this, and Nancy, yes, with this
Contour.
plan of ancestors,
Yeah.
and you succeed doing single series with more than one.
We were picked.
But showing that this
No, because it's good, Roberto. You said something which is true, but as Javier Spon will put, just too naive. Because if you restrict yourself to the right set of configuration, you can do for each set of configurations, you can try to do a perfect simulation which works there, and you change the environment, you change it.
Okay, let her continue.
No.
I wanted to quote Herbert Spon. It was like this. I learned all Spon was making asked that question to Herbert Spon in Paris, and Herbert said that this.
I prepared a blackboard. No. Okay. Okay, so the students, you understood the
We're very interested.
no, but the younger ones who never saw that in their life. Okay. Good. So there was the question of the initial condition. So because okay, so you understood the algorithm, and it's clear that in this way, if I want to simulate in this finite window f, so these are the neurons, and that is the time, whatever the time is. It's clear for each one of the neurons. You do this backward random walk until you stop either by regenerating or by hitting some link that you don't depend on. And that gives you a unique value to any of the neurons in there. And of course, there's also this question of coalescence. So it can be that you have another one here which chooses exactly the same ancestor here. And then, of course, the two of them will have the same value. And this also allows you to get something like a dependence-independence structure here, okay? Because, and that's what we are going to talk about this afternoon in the exercise sessions. Because if you have two couples here, so space-time couples, for which the random walks coalesce, then they depend. But if they have random walks that never coalesce, then they will be independent somehow, okay? So it's a nice feature. So he asked the question of the, so this will be a version of the stationary distribution of the process within this window. And the question is, why is this necessarily stationary? And then, well, the answer is the following one. Say if this is time 0, okay, and now I would like to construct the process within this window, but starting from some initial condition, which are all the spike trains on the left of 0. So for each neuron, I have exactly all the zeros and ones before time 0, which would be my initial condition. You understand what would be the modification of this algorithm to simulate from the process starting from little x, which is the initial condition. Because you just do the same thing. You have your random walks. Either they coalesce, either they regenerate before touching 0. But if some of them reaches the negative times, it just copies the value that it reaches here, provided you depend on it. Clear? Good. And if you take, so this gives you maybe another realization of the picture here, because you stop here and you don't continue exploring the past until you regenerate. And then to prove that this is necessarily the unique stationary version, you just show that if the time elapsed that you have in between here and here, say that is capital T, if that is big, then the probability of hitting the negative states will be small, because we regenerate after a finite number of steps, because it's a geometric distribution. The first regeneration happens after a finite number of trials. Okay, so if the time elapsed, capital T, between this window and the initial condition is sufficiently high, you will have the same realization here. Okay, it's a hand-waving proof because I don't have so many time. It's written in the notes. Okay, but that is the classical argument to prove that if you have a clan of ancestors method which stops after a finite number of steps almost surely, well, then it necessarily gives you a stationary version which is unique. Okay, because okay, good. This was the first part of the lecture. I just wanted to give this as a toy example because I like this random walk exploration of the past, and I thought it's easier to understand that, where exploring the past just means that at each step I choose a single ancestor, which is the neuron index and the time that I depend on. Okay, but this is a very special version of a more general construction, which is the clan of ancestors method, that I should not talk about here. I mean, it's Nancy or Pablo or Antonio or Roberto who should talk about that. Okay, so second part of the lecture now is to give you more general constructions that work even if you're not in this linear case. Because I said, point A, I'm in the discrete time linear Hawkes framework, and the linearity helps me to have these ancestors, which is a random walk exploration. In general, we can't use random walks. We will have set-valued processes, but the ideas are the same. We have to decide in each step which are the neuron indices and times that we depended on in the past. Okay.
You did this for finite number of neurons.
Yeah, no, that's not important, of course, yeah. So I erased the formula, because in my formula there was a 1 over n. If you have an infinite number of neurons, of course, the only thing you need in the formula is a probability distribution on I, of course. So the question, yeah. So exactly. Yeah. Yeah. So I said that was for finite. I had uniform distribution. That is not important. It could be any distribution on capital I, the set of neurons. The fact that I had geometric distribution, not important. No, any probability distribution on the past events would work. So
I want to point out a historical note that the clan of ancestors, I'm working on that because this is the transcriptions in probability terms of the cluster expansion.
I was afraid of that. I was afraid.
Yeah. So if you restrict to what that was it. So that I can invert it, and maybe there are some cluster expansion algorithms, arguments.
Tu connais l'expression française, mais quel culot ce mec! Quel culot ce mec!
So maybe for the historical, I tried to put some literature in the notes. So I cited, so there is a paper by Pablo from 1990. I don't know if this is the first one. So this clan of ancestors method. Then Pablo Mas Martinez Ney.
Yes.
Yeah. But the paper that I know most is the one by Francisco Metz, Roberto, and Pablo. And then Nancy has worked a lot on that. And where I really learned it about is the lecture notes that Antonio, Pablo, and Roberto wrote together. And you really have to put it on the internet somewhere.
It was wonderful because the team was agreed to change entirely the presentation. It was wonderful. I remember Pablo said, "Oh, what good idea." Pablo refused to present the way we wrote in the book, and saying that we were betraying.
So it was really a collaboration among Latin people.
Yeah. So you have to put your lecture notes somewhere, okay? Because it was, I think you didn't really publish it, no?
No, it's not bad.
You should do that. Okay. Yeah. Okay, so second part of the talk is Kalikov decompositions, because I want to prepare tomorrow's talk and the exercise sessions by Sophie. So I go to a more general frame. So say that is I always forget if it's W or let's say it's W. So I come back to the variable memory frame where each neuron is collecting inferences of presynaptic neurons since the last spiking time. It's evident if I add this already in this Hawkes frame that this random walk doesn't work anymore. It's clear, no? Because if I only depend on anything that I had since the last spiking time, well, it's not enough to have the information which neighbor I chose. I also have to know what I had as a history since when he did not spike, okay? So already putting this into the linear Hawkes model tells us that this does not work anymore. Good, so, but I will take something more general. So I have, so I is anything now, and I will write PIT of one given x, that is the probability that xt of I is equal 1. Yeah, given that the whole past, so since t minus 1 up to minus infinity of all the other neurons, okay, so that is the complete spiking picture, is equal to little x. So the little x here is an element of 0, 1 to the power I times z. And I'm not very precise here because of that. This x is only the projection of the total configuration before time t minus 1, including t minus 1, but I will not write that, okay? Good. And the model we have is the one that we studied together with Antonio in a paper 2013. The first we wrote on neurons, I think. So it's still the same kind of model. So it's phi I of And then I have the sum S equal Li t minus 1 plus 1. So what is this? This is the last spiking time of u and I before time t minus 1. Okay? And I start one time later because when I spike, I'm equal to 0, and then I start accumulating jumps. And then I have the same kind of t minus 1 minus s xs. And phi is now anything. It could be nonlinear, okay? Such that the w's can also be negative. So Li t minus 1 is the last time s before time t minus 1 such that xs of I was equal to 1. So last spike of I before time t minus 1. So that is the main difference with respect to the Hawkes model that I had, where I started at minus infinity, which was a continuous model with respect to the past. Okay. Here I erase everything at each spiking time. Okay. So I will suppose if I is infinite, of course, I need to suppose that the w's are somehow summable. And we also need to impose that the gi's are summable as a function of time. So the L1 norm, the discrete L1 norm, has to be finite, such that this is all well defined. And I will, as usually, suppose that the phi's are Lipschitz continuous. Well, it's not completely necessary, but it's very convenient. Okay, good. So if you write it like that, so this is the model. It's clear now. So it's the discrete time version of what we had before, except that we have now some general dependency on the past, which could be non-Markovian. We see that we have a notion of interaction neighborhoods. I think I did not so much speak about that for the moment because I was in this mean field frame. But here it's clear that I is influenced by all those for which the w's are different of 0. I don't take them equal to 0, 1 anymore. It can be positive, negative, weighted. Okay, but if some of them are 0, that means they don't influence I. So I will write V, well, dot to I. These are the presynaptic muons to I. Okay. And it's clear that this transition depends only on the restriction of x in the space direction to this neighborhood. Okay, good. So the idea is now to try to write these transition probabilities as before as a sum of other transition probabilities which depend on less events, okay, which are more local than this one. It's not local because it depends on the total path, at least up to the last spike. And so I have to say what I mean by local transitions. So the goal is write T of dot given x, so 1 given x or 0 given x, which is the opposite event that I don't spike, as a sum of local transitions. And to define the local transitions, I have to introduce neighborhoods. And the introduction of neighborhoods, it's not uniquely defined. So neighborhoods, okay, or local neighborhoods. So that will be finite subsets that I call Vi of k. So I'm interested in U and I and in its transitions. And k is something that you could interpret as the diameter of the neighborhood. So Vi of k is a finite subset of I times the positive times. So I take positive, so these are the Newen indices that I depend on. And these are the times that I have to look back into past, okay? But I take them positive, it's clear. So if I'm at time t and I choose a neighborhood 3, that means I have to go to t minus 3, okay? To look into the past. So it is a countable collection of neighborhoods. So I take k bigger or equal to 0. In general, we choose Vi of 0 equal to the empty set. And then we choose them such that the union of all of them includes this times all the times. I write it down. So the union of the Vi of k should include V dot to I including I, because I need I to have my last spiking time, times all positive times, okay? So in my random walk examples, the neighborhoods were singleton neighborhoods, okay? So Vi of k was something like a single Newen index and a single time. But here, usually we will take neighborhoods which are sets of a certain size, okay? And the choices that we have to use, it depends on the models we have. Okay, so then the definition. So a Kalikov decomposition of P IT, and it is always a decomposition with respect to the choice of the neighborhoods. So with respect to the neighborhood family Vi of k is, so I first write the decomposition and then I explain the terms. And then Roberto will tell us if this is really the cluster expansion. So it's a representation of the transition probability. So little a is either 1 or 0, absence or presence of a spike. X is the past, okay, times and indices of the Newens. And so it's a representation of this as a sum. I sum over all indices of the neighborhood. So the little k is the k of the Vi of k. And I write the following. So lambda I of k is the probability of choosing neighborhood k. And then I have a transition that only depends on x within this chosen neighborhood. So I should write x. Yeah, it's not completely exact because it's the Vk which is shifted by t. Okay, but you understand what I. Okay. So the lambdas are probabilities on the choices of the neighborhood. So they are in between 0 and 1, so probabilities. Once I have chosen my neighborhood, that means, so this is T, that means that I have to look only in the neighborhood Vi of k, which is shifted by T. I mean, I look back into, if k is 3, that would mean T minus 1, T minus 2, T minus 3. So I look on X only within this neighborhood, and I do a transition. So this is a probability in A, but depending only on X within this local neighborhood. Okay, is it clear? So it's pretty much the same thing as before. Before we were choosing neighborhoods, which was choosing the time index and the index of the neuron. And the probability which was associated was a deterministic one, because in the imitation model, we just copied the model of the influencing neuron. Okay, so in the first model, this was not a real probability. It was a degenerate. It was a Dirac mass. Okay, so we have to add this randomness here in general. But apart from that, and apart from the fact that I depend on maybe more particles, not only one, but on all the particles within this region here, well, I still have the same interpretation. Okay? So the most important point, and that is something, so is clear, no, I should write it here. So depends on X only within Vi of k shifted by T, and then looking back into the past. Yes, I think I wrote it. No. No. So they're supposed to be finite. Yeah. In most of the examples, they will be taken increasing in k. So I start with very small neighborhoods, and then I successively explore the past and the neighbors, but that's not necessary. So Patricia called that the nested neighborhood. So if Vi of k is included in Vi of k plus 1, so I'm exploring more and more the space. But you saw in the random walk example, they are not nested because they are singleton ones, but they are all finite. Okay. So I'll give you an example. So it's clear what is the good event here is the choice of k equal to 0. That is exactly the regeneration that we had before. So we mark k equal to 0 is the regeneration because I chose Vi of 0 to be the empty set. By this I mean that if I happen to choose the empty neighborhood, I am able to update independently of anything else. Which also means that the higher the value of lambda I of 0, the better it is. Okay, and if lambda I of 0 is not equal to something strictly positive, well, then I don't know how to do my algorithm, of course, in this framework. Okay, so for everything to work, lambda I of 0 strictly positive will be needed. Actually, we need it rather big in front of the others. So we want lambda I of 0 to be big, and then we want the choices of large case, if it's nested, to be less probable. Okay. Okay, so I wanted to give an example. So say I want to have the position of a neuron which is this one. Okay, so there is time as before, and so I want this one. So I choose the neighborhood with lambda I of dot. So say the neighborhood I chose is something like that. So I have, say, 4 neurons that I would potentially depend on. Okay. So to know this one, I have to know the positions, which means the zeros and the ones of all the neurons in there. So I iterate for each of these independently of anything else. I choose the neighborhood and I continue. So say this one chooses this. Sorry. So this one chooses this, possible. This one chooses this. This one chooses to update independently of anything else. So this means a choice 0. And this one also chooses that. Okay. And then in the second step, we need to have the positions of this and of this. No. And this one has already chosen to depend on that. And if we are lucky, and this one is updating independently of anything else, we are able to have the position of this. And this is how the algorithm works. Okay? And notice that in this case, it's not all ones in the end, because these are true probabilities now. It's not only Dirac masses. Okay? So there is a real choice associated to these ones. Okay. Good. I'm not sure that I should write the algorithm. I think if you understood that, it's pretty clear. Maybe I just write one line. I don't write the algorithm. It's the same as before, except that instead of having Bernoulli random variables and these i's and the t's, I will do the following for each neuron index and time. I associate something that I call O, that is supposed to be a calligraphic capital O, like offspring. Okay. And this is a finite, it's a random finite subset of I times the past before time S. Okay, and it's actually the neighborhood that I have chosen. This is a subset of I times minus infinity up to S minus 1. It's a random subset. And we have that O GS is equal to all I, say, U, such that I have to think let me look it up. I S minus U is in V J of K, and this is with probability lambda J. Okay. It's because I decided to make the times in my neighborhood positive. It's the time I have to look back into my past. So this is a positive time, and that means that U is just before S. Okay. So this is what I have. Well, anyhow, okay. So I call these the ancestors of the couple JS, and it is clear that my random walk will be replaced by a set-valued process, where at each step of the random walk, I replace the couple JS by its offspring set, and then independently of anything else for each couple of neuron times time in this offspring, I replace by the offsprings and so on. So pretty much in the same spirit as this one. Okay. And is it okay, or was it too fast for the mean field specialists who maybe never saw this? Yeah? Okay. So the point is, if I'm lucky, this procedure will stop after a finite number of steps. And you see why it should stop, because the regeneration probability is sufficiently high uniformly with respect to all neurons. And this is done, well, you can do very rough arguments by saying, in this setting, I replace each neuron, JS, by all the people in this offspring set, which is a branching process. Okay, so I just compare that to a branching process, replacing JS by all the positions within this random set. And if this branching process is subcritical, then we are sure that we stop after a finite time, almost surely. Of course, that is a very bad estimate, because you see that we have overlap. It's not at all a branching process. In this picture, you see I chose this one, but this one chose this one as an ancestor. So we don't have necessarily independent updates, we have overlaps. So imposing that the branching process is subcritical is certainly much too strong as a condition, but at least it's sufficient to make the algorithm stop. Okay? Any questions so far?
Is there an easy way to write a condition of subcriticality in this generality?
For the moment, it's very. For the moment, it's really very abstract, because the condition would be that the supremum over all I of the sum k equal 1 up to infinity lambda I of k. And so with probability k, I choose vi of k. Okay. So that has to be less than 1. Okay. So this is the number of supports which are in this finite set. Okay. But of course, I didn't say anything about how do I choose the vi of k. That really depends on the model you want, on the parameters that you have. So maybe in the last 50 minutes, I should talk a little bit. I don't want to go into the details, but which are the conditions? So we saw in this linear Hawkes case, the decomposition was already given by the way the transitions were given. We didn't have to work for having the decomposition. Okay. Here we have to work a little bit because, well, I mean, the definition of PIT of one given x is not there anymore, but it's something complicated and it's not so clear how we should do it. Okay. So the first thing is that a sufficient condition for having this Kalikov decomposition, for having existence of that, is the continuity of these transitions with respect to the past. This is a strong condition, it's not necessary. Sandro has worked, well, did you work on these kinds of questions? Yeah. Huh? So if it's not continuous in the past, it can also exist, but it's easier if we suppose that we have some continuity, which basically means summability of the interaction and Lipschitz continuity of the phi's, which makes it easier. Continuity of phi. I'm not very efficient in using the blackboard, but okay. So existence of the decomposition. Okay. So in the sequel, I suppose that my neighbor, it's always with respect to a given choice of neighborhoods. And if I'm adopting this continuity point of view, then it's very convenient to take neighborhoods which are growing. Okay, so take nested neighborhoods. By this I mean that vi of k is included in the next one. So they are going, okay? And I suppose my transitions to be continuous in a strong sense. That means if I compare P of 1 knowing x and P of 1 knowing y, and x and y coincide in the neighborhood of size k, then as the size tends to infinity, that should converge to 0. Okay, so more precisely, so P it of 1 given x is strongly continuous with respect to x. That means, well, I didn't speak about that for the moment. You see that the time doesn't really play a role because I have homogeneous transitions. My dependency on the past is always the same. I just have to shift all the configurations. So in order not to be obliged to write the time everything, I will be interested in the transitions given the past before time 0. Okay? And then in the sequel, I don't write that anymore. Good? So I will just have P of 1 given x, and x is the total past strictly before time 0. So -1, -2, blah, blah, blah. So it's continuous with respect to x if the limit as k tends to infinity of the supremum of Pi of 1 given x minus Pi of 1 given y. So I take the maximal difference between the two, given past x and past y, supposing that the two are the same on the neighborhood k. Okay, so such that x is equal to y on the neighborhood before. Okay? And I suppose that this converges to 0 as the neighborhoods explore the total past and total interaction neighborhood. Okay? This is something which holds true if the W's are summable, the GI is summable, and the phi's are continuous. Okay, so maybe I should give this as an example. So we mark if the sum j, w, j to I. So this is the sum of the incoming interactions. This is finite, and sum of the dependency on the past also, plus phi I continuous. I think it's sufficient. If you want to have estimates, you have to take it Lipschitz. Phi I is continuous, and that implies that we have this continuity. Okay, good. And then I just try to give you an idea, at least, where the lambdas come from. And then I stop. Okay? I'm not writing the exact construction of the decomposition because it's complicated. You have to do it at home by drawing pictures. And maybe I already give a comment because tomorrow I will speak about the same thing but in continuous time. And the amazing thing in continuous time is first of all, it's more difficult. to prove that it exists. Okay? But the exact formula for the decomposition is easier to obtain. And the algorithm to stop is also easier. We will not need tomorrow, well, somehow, this condition here. Okay, I will come back to that tomorrow. Okay, so under these continuity conditions, I will introduce something which is, well, I write the formula and then I try to explain them. So R is something like regenerating. Okay, that's why I use it. So I0 of 1 will be the minimal probability of spiking for neuron I. Okay, can be 0. So this is the minimal spiking probability. In the same way, I will have the minimal non-spiking probability. Good. And then I do the same thing for increasing sizes of the neighborhoods. So Rik of A given X, for any A, will be the minimal probability of A given any neighborhood which coincides with X up to K. Okay, so this is the infimum of all Y, which are equal to X up to K. Up to K means in Vi of K. Yeah, exactly. Of P I of A given X. Okay, so the minimal probability of A, Y, exactly. Okay, so outside the neighborhood K, I do anything. And then I just look on the minimal influence of that on the neighborhood. Good. And then I will just associate to these guys the total mass. So I will have alpha I K of X, which is the sum of them plus okay. And since I have nested neighborhoods, okay, so if I take this infima and the neighborhoods are bigger and bigger, that means that I have things which are growing. This is important, okay? So if I draw a picture, so this picture now is a picture on the uniform random variable on 0, 1 that I would like to use to perform a transition according to that. Okay? So this is 0, 1, and on this 0, 1 I will just write. So for example, suppose that is alpha I alpha I 0. This is alpha I1 of X, something like that. So this is for the total condition X, and then here I have the same. Yes, but I want to have the total mass here on my picture.
Yeah. So you have alpha 0, and then you have alpha 1 is the difference between the first line and the second line.
No, I didn't define it. It will be the lambda, the difference. I know. I wanted to write these guys for fixed x and for fixed y. Okay. So this is the same, but say maybe this one is bigger, and so on. I could do that for any neighborhood and for each instance of the case. Okay, this is 0, 1, 2, and they are increasing because the neighborhoods are nested. Okay, so what I will do is, instead of considering these, I will take the minimal alpha with respect to all x's. And this is what I'm going to write down here. So of course the first one is always the same because it doesn't depend on x, alpha I of 0. And then the second one, say it's something which will be here. So this is alpha I 1. So that will be the infimum of all alpha ik with respect to all neighborhoods, and so on. Okay. So alpha ik is the infimum of all x of all alpha I k of x. Good. So what does it mean? That means if your uniform falls into this time interval, that means that you can make an update independently of anything else, either 0 or 1. If the uniform falls in here, that means that independently of any configuration, you're able to make an update depending only on neighborhood 1. Okay, if it falls, and then I will have alpha I2, say it is here, and here you are sure that you can make updates by looking only on neighborhoods 2. It's clear that that is very pessimistic, because you see that for the y neighborhood, actually up to here, I only needed to look on neighborhood 1. But since I have to look uniformly on all possible neighborhoods, well, at least here I'm sure that the choice can be made by looking on neighborhoods 1, 2, 3, and so on. Okay, and that is the way the lambdas are defined. Okay, so the lambdas, so this is lambda 0. I think I called it like that. Sorry for my notation. The length here is lambda I of 1, because here I make decisions depending on 1. Here I make decisions depending on 2. I'm pessimistic, okay, but it works. Okay, good. This is the way we define the lambdas. And the p's, well, we have formula for them. They're explicit, but not nice. And maybe last remark, we also have a control on the decay of the lambda of k, depending on the q's, on the tails of the interactions outside vi of k, if the phi's are Lipschitz. Okay, so at least you know that if the interactions decay sufficiently fast, that means the lambda of k is also decay rather fast, which gives you at least the hope of having your subcriticality criteria be satisfied for good values of the parameter, because that is, of course, an important question. Okay, good. I stop here, and I will continue on that tomorrow in continuous time. So for point processes which are driven by Poisson random measures.
I want to add that this way of proceeding, you guarantee that you maximize the probability of using low orders. So this is the largest way, the alpha 0, the largest probability of using 0, etc.
Yes.
Even that.
Yeah. Yeah.
Because it's not unique, but it's
no.
to change things. But
okay. So the Kalikov decomposition is not unique. You can think about Mauro did that. I mean, Antonio cited all the Mauro papers by saying that he always did better. So the question is, given your transition probabilities, what is the best choice of the neighborhoods? Okay, so you answered to that in some of your papers, I think, no?
Yes. Remind me something.
If we might,
I want, so, started by the question, is lambda the smallest one in the sense of gives
the maximal way,
this is a random variable taking integer values. So these are ordered by so that's maybe it is not the one with the smallest. Most of the time it is, but it's not. You can afford not to couple as much as possible at the beginning to be able to couple better afterwards. So I think that you could produce a situation in which this is not it's a default, of course. That is assumption, but it's not the smallest one.
Clusters and coupling.
this is total variation coupling, no?
But I think that's
No.
it's kind of greedy.
Yes, yes.
Ah,
Yeah, so what you want is to minimize the regeneration, the stopping time,
Yeah.
and that's not automatic. It's the most natural choice.
There is an important question here. The condition on the sum of the absolute value is not a good condition. Because the biological condition is a balance between the positive and negative.
yeah.
So
Yeah, but then
it's difficult.
then you have to take all the cancellations into
Yeah.
consideration.
The first time we present this article at Marseille, a student asked us, but professors, you are putting a condition, it's not realistic. Because everybody knows that you have a balance. And I said, yes, so.
Just
Okay, let's have coffee.
Okay, let's start with the plenary talks of this morning. First speaker is Guilherme Costa from Federal University of Rio de Janeiro. To speak about sub-switching Markov chains. Please.
Thank you very much, Sandro. So it's an honor for me to be talking to you, especially in this context. So it's before starting, I just had to say a few words because I mean, especially after yesterday that Florencia was giving a very nice speech. So I think no matter what, it's really impossible to be as good at as she did yesterday. So so I met Antonio in 2011, I think, when I arrived here in São Paulo to do my PhD. And I mean, I don't know, I had this feeling that I would come here to São Paulo and then just go back after finished my PhD. But somehow I couldn't be so more wrong about that. And somehow Antonio is responsible for this. Because, I don't know, he presented me a completely new world about many things. And that I feel that I needed to explore. Because thanks to him, I met many incredible people. Many of them are still here. And so I've learned a lot from him. I'm still sure I will learn much more yet. And just to conclude, I don't know if it will be a good thing, but if I'm really sure that if I try to fit some context-free model to predict what I'll be doing in the next future, I think Antonio will be appearing in all the contexts of this tree. So so I don't want to say more. So thank you very much for everything, Antonio. And so what we'll be talking today, it's switching Markov chains. Is something completely different from me. So I have been working much more in models in mathematical neuroscience, and when but then I moved to Rio de Janeiro, and there, for example, most of the people were not working on mathematical neuroscience. And for example, Julio here is a specialist in the models on Handel graphs and Brown walks, etc. And because of this, we started discussing together with Sandro and Takahashi something about this Markov chains related to let's say to learning of animal behavior somehow. I'm trying to explain this in a minute. I just want to mention that part of this talk will be based in these two papers. One is already published in the ESPA, and this one should appear soon on arXiv. Okay, soon, I mean by the end of the month, I expect. So let me try to give a very short motivation for that. So this is my cat, and when I observe my cat, he most of the time is sleeping. Okay, most of the time is sleeping. I think many of you that have some pet will say that similar things happens with you. But then when he is not sleeping, what I observe is just a few behaviors. So for example, he's eating, licking itself, or playing with some toys, and etc. I mean, just that, okay? And so somehow, this is just a very quick motivation to has been addressed in this context of Markov decision process, okay? I won't say anything about this Markov decision process, but really the idea here is that the predominance of a subset of behaviors or actions, in fact, this is what the term that they use, it's induced or occurs due to some learning mechanism, okay? Because somehow at each step that I do, at each time the system is a given state, and then I do some action. In respect to this action, I do my next movement, but also I receive a reward with respect to this movement. And the learning is really, I mean, so there is somehow the learning induced by this reward. Okay, and at the end you learn some behavior, meaning that you do just a few set of actions due to this fact. Okay, and another thing is, somehow is less important, is that the set of behaviors or actions are finite, let's say, and often very small. Okay, and what we just want to mention here is actually this fact of learning through reward, I think is not just the whole story, in the sense that it's possible to observe only a few dominant behaviors despite any lack of learning, and even if the set of behaviors is huge. And this is somehow what we wanted to mention here. And as you see here, is related to somehow to the notion of metastability. Okay, that's what I want to tell you. Okay. So let me give you an example, the first example. So let's say we take 2 points in the 0, 1, so A and B. And here A is strictly positive and is smaller than B, and actually is smaller than 1/2. So I mean, what is important here, I mean, could be in this setting here, or could be also in this setting here, okay? So let's fix these guys. And then we take mu, the uniform distribution on this interval 0, A, okay? And for me here, this interval, I will explain in a minute, will be my set of behaviors, okay? All right, what is the model that we consider that we are calling this self-switching environment random walks? So this model is defined in several, iteratively, so to speak. So and the number, I will index each step by I. So for each step I, what I do is I choose some parameter theta I according to this distribution mu, which is uniform, and I do this independently, okay? So once I do that, what I do, I consider a random walk on -n, so -n to n, where the transitions are indicated in this picture, okay? And so here it should be theta I instead of theta, okay? So this is a mistake. And so what this random walk is doing somehow is, if I take a vertex which is to the right of the origin, so I will jump to the right with probability theta, and to the left with probability 1 minus theta I, actually. And here's I do the reverse. If I take a vertex here, so I will jump to the left with probability theta and 1 minus theta to the right, okay? So I will start a random walk here from the origin, and I will look, so I will observe the path, and the path that the random walk does, until it reaches, so starting from 0, it reaches the boundary, -n or n, okay? And I call it this time tau I, okay? And at this moment, I repeat this procedure again. So I reset the random walk to 0, and I choose another theta independently, uniformly, and I wait until the random walk reaches -n and n, and I record the second time tau 2, and etc. Exactly. Yeah, is the number. Yeah, I here stands for the trial.
And then go to the right with theta I.
Mm-hmm.
If you are on the positive, to the left, this one.
Yeah. So let me just to make a picture here that will be important in a minute. What really matters at the end of the day for this, correct me if I'm saying something stupid. So if theta, for example, is larger than 1/2, I have the tendency, I mean, starting from the origin, I will somehow hit very fast at -n or n, right? So somehow if I do some potential here, will be something like this, no? It's like at the beginning I'm here and then I soon go either here or to -n. And if it's the opposite, it's like I have a well, right? And I'm starting here at the bottom, and that's the picture that you have to have in mind. Okay, so this is the first thing. And then after building, I mean, doing these many steps, I can build, for example, what we call this state or behavior process, theta n of t, which is defined in the following way. So this state process will tell me at which parameter I am at a given time, at each parameter theta I am at a given time. So for example, when I know that I will be at theta 1 between 1 and tau 1, I will observe the state theta 2 when t is between tau 1 and tau 1 plus tau 2, etc. Okay, I do that there. And this is the dynamics that, this is the process that we wanted to understand. So it's somehow is coupled. So I have this location process, which gives me what the random walk is doing. And at the same time, I observe the state at which I am. Okay.
No. Can you explain again?
Here? Okay. So here is just to, if we observe, for example, the transitions, just to understand what is the behavior of the random walk depending on the choice of theta. So if theta is greater than 1/2, somehow I have a tendency to reach -n or n very fast. And so you can imagine that it's like I am here at the top of this mountain, and then I can go very fast to the bottom, which is -n or n. And here is the reverse. You need to climb all the mountain somehow. Okay.
For a smaller interval of time.
Exactly. Okay. And these thetas are the different behaviors for us. Okay. All right. And here it's important for us, that's our interpretation, maybe it's wrong, that we say that this system doesn't have any learning role, because the parameters, the thetas that I choose independently, no matter what no matter what happened before. Okay, so there is no learning in this sense. Okay, good. And here's something which for us at the beginning was surprising somehow, which is this emerging dominance phenomenon. That is the following. So if you observe this state process for a very long time, right? And somehow the n, which I'm using here quotation marks, is the volume or the size of the system is very large, right? What happens is this state process, it will be concentrated at just one state, which in this case is A, which is I don't know if you remember, we had this interval AB here, okay? And we are claiming that the state process somehow will be concentrated at this unique somehow behavior, which is given by theta equals A, right? So in this phenomena, we were calling emerging dominance phenomenon. Okay. Right. So let me try to formalize this. So to formalize this, we define what we call this empirical occupation measure. Yeah, half could be included, and in this case, it's I think it's quadratic somehow. Yeah, sorry, half could be included. You're right, Antonio. But then it's like it's flat somehow. Right? So let me try to formalize this. what we do is, for each interval, let's say A, containing this in the interval A, B, we define what is the empirical occupation of the measure of the set A with respect to the state process, which is defined in this way. So imagine that I observe the state process from time 1 to t, and for each interval A, I'm just computing the frequency of time that the state process is inside this set A. Okay? It's something, maybe I do a picture here. So this is time. So let's say here's A and here's B. And I take some interval A here. And my state process, remember, is something like this, no? It has jumps. So this is theta 1, so this will be theta 2, theta 3, etc. Okay, so if I fix some time, and here I'm just, up to this time, I want just to know how much time, in average, this state process stayed inside the set A. Okay, so this is the occupation measure. Right?
Where are you at time n?
Yes, I could. We could. Yeah, it's the empirical. And the first thing is, if we go back here for this informal definition of emergent dominance, I said that if we look at the state process for a very long time, for large times, so this means that I will first observe the behavior of this occupation measure when the n, so n here is the time, goes to infinity, or is very large, goes to infinity, and then I do something with respect to capital M. Okay. So the first thing to show, which is not, I mean, this somehow is very classical, is that this occupation measure, so this is random because the process is random, right? It converges when time goes to infinity almost surely. So for every A, converges something to a given measure, which we denote Pn of A, which is somehow is just proportional. So here I'm just summing over all possible thetas, right, which are in A, and then for each theta I have a weight associated to this parameter, which is just, so Mn of theta denotes the expected time that the random walk takes to reach minus n or n when the state governing the transitions is theta. Okay, so that's the average time, and here is just renormalizing. Okay, so that's this limit occupation measure. Okay, and the proof of this, I mean, it's not new. We are just somehow reusing what is usually called the law of large numbers for renewal process, and then that's it. Okay. Okay. Good. And somehow now, what I wanted to discuss is that this emerging dominance phenomena is equivalent to say that this measure here, Pn, will be concentrated, will be very close to the delta Dirac at A. Okay, so observe for a very long time, and then the volume is very large. The process will be concentrated at A. I can formalize in this way. Okay. Okay, then so that's the theorem. So this is the first theorem that we had, that this Pn converges weakly to this delta Dirac at A when it goes to infinity. And the proof is very simple, and now we will realize that metastabilities are already appearing here. I mean, it's something, maybe it's just a different way of seeing it. So let me try to explain the proof very shortly. So recall that the transitions are like this, okay? And then what is really important here is to observe the behavior, this M and theta, which is the average time that the random walk starting from the origin takes to reach minus n when the transitions are theta, okay? And the thing is, if theta is larger than 1/2, we know that the time it takes with respect to n is linear. Okay, so this case here is linear. When theta is 1/2, this situation here, the time is quadratically with respect to n, so n squared, right? And now in this situation here, when theta is smaller than 1/2, what we have is that the growth, of mn of theta is exponential with n. So it's e to the n times some function which depends on theta, right? And this function, I can make it, I don't remember the expression, but it's something which looks like this. It's something like this. It's decreasing, and its maximum value is at a, okay? Okay, and so somehow if you put all this together, you see that the time that the system will, where the system will stay for most of the time is really for theta equals to a. And so this is explaining why somehow the state process will be concentrated at the state A. Okay? Good. So that's the first example that we have, sorry. And now I'd like to discuss a second example, which we can show, for example, if we could prove emergent dominance for 2 or more states. Okay? So now I try to go, and just to state more easily the next theorem, let me just to put this definition. That is what we mean by emergent dominance at some states. Is just the following. So remember, we have this Pn, right? And then we'll say that there is emergent dominance at states theta star 1, theta star k, with these weights W1, Wk, if this measure here, Pn, converges weakly to this mixture here. Okay? That's it. And so let me now tell you a second example where we can show, for example, emergent dominance in two states. So again, we have this interval AB, okay? But now just will be important for us that A and B, so A is really smaller than 1/2 and B is strictly larger than 1/2, okay? Then again, I take mu, the uniform distribution, and I do something very similar to the first example, okay? So at each iteration, I will choose some parameter according to mu independently. Now what I just change is the dynamics of the underlying random walk, okay? So now the random walk is from -2n to 2n, okay? And given theta, the transitions are as follows. So here is kind of a mess to explain, but let me try to just summarize here in the blackboard what's important. What is really important, and let me just say, I hope I'm not saying something wrong here. So again, if I take theta, which is larger than 1/2, so what happens here, if theta is larger than 1/2, I will have a tendency, so let's look at here. I'll have a tendency like whenever I'm here, I have a tendency of going to the right, okay? And for example, whenever I'm here in this position, I'll have a tendency to go to the left, okay? So somehow the dynamics here is that the random walk will stays around the state -n in this case, okay? So -n is around here. We'll build it in such a way, okay? And for theta is smaller than 1/2, I mean, you need to check later, but the idea is that the process, the random walk, will be concentrated around n in this case. Okay, so the random walk stays okay. So that's the most important thing here for this picture. Okay. Any questions? Well, and again, so how is the dynamics? I start from 0 for a given theta, and then I wait until the random walk reaches -2 or 2. I record the corresponding time it takes to reach the boundary, and I keep doing this many times. Okay. Right. And then for this process, I can go back to the occupation measure. We can show that the occupation measure, if I look to for a very long time, this will converge to some measure, Pn, okay? And the point is, in this case, the Pn now can have different behaviors depending on basically the distance between A, the points A, to 1/2, okay? So let me maybe state this here. Because the main point here, if you look to the description that I gave it here, is that no matter the theta, now the time will take to start from the origin to reach the boundary will be exponential, no matter the parameter theta, okay? Except maybe for theta equals 1/2, okay? So in this case, I know that always the time will be of the form n times age of theta, and now age of theta now has this shape that I draw here, something like this. And so the point is, if A and B, they are at an equal distance to 1/2, I know that these two behaviors will survive somehow with equal weights. And now if A is, for example, here, then we'll observe just emergent dominance at B, okay? And if it's the other way around, if it's A is like this, like here, then we observe the emergent dominance at A, okay? So this is more or less the theorem that I'm staying, and the proof is very much like I was saying right now. Okay, good. Okay, so I skip this. So far, I don't know, Sandro, how much time do I have? Okay, maybe I'm going faster than I should, but okay. So far, let's summarize what we have. Is we can prove that emergent dominance occurs without any learning rule, okay? So what we want with these results is to just to suggest that the learning is not the only mechanism that modulates the preference of one dynamics of other. Yeah, no, but A and B.
Your rule.
No, but yeah. But I mean, the point is, yeah, perhaps. Yeah. And somehow, I mean, for the proofs, essentially, the main ingredient is this notion of metastability, right? Because again, I mean, and it's hidden here, right? The time it takes to reach minus n or n is exponential. This is another way of defining somehow metastable states, right? Right. And of course, I just want to say that these two toy examples are just a part of some very general results that we have, okay, in the paper. And I just invite you, if you are more interested in to know which type of results we have, I invite you to have a look at the first reference. Okay. Okay, now, so I don't know if you have some questions up to this point.
How do you define a metastable state?
Well, I will define, well, yeah, I mean, it's, you are the specialist, so somehow I would say that in this context, in this context, I would say it's just the thetas for which the time it takes to read the boundary is exponential, but maybe it's a very, I don't know. I'm not a specialist, so. Okay. Yes. And for, yeah, somehow we are saying in this case that this emergent dominance, the phenomena which is behind is this metastability. I apologize for Roberto if I'm not defining correctly what metastability is. Okay, so yeah, so that's the main.
There is a point of confusion among people in probability. Confusion about the poor people in probability. The problem is the metastability is when you are in a state which is not the equilibrium state, and then you go to the equilibrium state. Metastability is not when you are in equilibrium jumping from one part of the phase space to the other. This is not metastability, this is tunneling. Tunneling.
Okay.
And the distinction is important if you want to talk to physicists.
Yeah, sure. Thank you very much. Yeah, so I apologize. I mean, it's okay.
Long time ago, Enzo came here, São Paulo, and we were looking for someone who would work with him because Paris was occupied. So I said, okay, let's. And then he told me that Joe Leibowitz was interested in defining metastable states. Is a way he defines stable states. So what was the way Joe Leibowitz described? So you prepare your experiment, and you are there, and the reaction does not occur. So you wait, you go to take a cough, nothing happens. And suddenly it happens. So there are two things, something which seems stationary, but it's not. And the time it stays there is unpredictable.
Yeah.
So that's why Joe Leibowitz.
Yeah, but also that when it happens, you go to the
Okay. So I'm using Leibovitz's definition of stability. Okay.
The best example you make is you put milk to boil, and wait, nothing happens, then look at it, and it goes away.
Okay. Okay. Now, so to conclude, I just want to give you a third example. Okay. Which in fact was the first one that we, with Sandro and Daniel and Julio, we wanted to investigate when we started discussing all this, okay? And which is the following. So it's like more, well, it's not more complicated, but the notation is a bit different. Now, I don't know what I changed, but so imagine that this lambda here would play the role of my interval A and B, okay? Except now it's any compact set, if you want. The important thing is one is here, and I will explain in a minute, okay? So again, I take mu uniform probability measure on this guy, okay? And now I will do something very similar to I was explaining before. So I want to define this self-switching random walks on Erdos-Chernyi random graphs in this case. And so what we do is the following. So instead of, so the thetas before now will replace by lambda i's, okay? So now at each iteration of this model, I choose lambda I according to mu independently. Yes, yeah. Yeah, one is lambda, yeah, okay? And now, once I have chosen this lambda I, what I do, I generate a Erdos-Chernyi random graph with n vertices, capital N vertices, and the edge, the probability of connecting a pair of vertices, now it's lambda I over n. Okay, so now I'm choosing the lambda I here, this case. Okay, and once I do that, I take, for example, any given vertices of the vertex of this graph, let's say 1. So now that's this vector vertex, sorry, will play the role of the origin. And what I do is I fix the random walk starting from 1, and I run it until it goes back again to this vertex 1. Okay, and I record the corresponding time it takes to do that. Right? So again, in this context, I could go to the Coefficient measure. I see as it behaves when time is very long, and then I can show that this also converges to some measure Pn, which depends now on the size of this random graph. Okay? And the conjecture that, yeah. And the conjecture that we had at that time was that there would be emergent dominance at lambda equals 1, which corresponds to the critical value of the Erdős-Rényi random graph. Right? We had this idea, and basically what we were saying is, okay, if lambda is smaller than 1, so the size of all the connected components is very small, so the random walk will go back very fast to vertex 1. If lambda is strictly larger than 1, then the graph is connected, so I mean there is it should go back back very fast to the vertex 1 as well. And at the critical, if I look locally, it looks like a tree, so in this regime where the random walk would take more time to go back somehow. That's what we had in mind. Okay? And the question is, who believes that this conjecture is true? Raises his hand.
No, I just found an article, a review article by Bolovas. I sent it to Eva, which tells us that it is not actually true that lambda equal 1. It is a small interval. I didn't finish reading it there. So Bolovas says the article by Erdős-Rényi is a great article, but it's not entirely correct. And there is a thing about the way it changed that 1. It's not the size of 1. That's what I understood. So I'm afraid to say anything, but
yeah.
I think it's reasonable.
So that's what we wanted to study at first when we started. Okay, I'll be happy. And then it turns out that this conjecture is false. It's false, in fact. And in fact, so that's why somehow we decided. So up to that point, I mean, up to the previous slide, it was really the content of the first paper, and that's why we are writing the second short paper to explain this, which is related to the first question. And what I want to say here, it's somehow this measure Pn, in this case, it won't be concentrated at 1. And in fact, as I will try to explain in a minute, that somehow what we observe when this n is very large is just parameters for which the random graph is in the regime of in which the random graph is in the supercritical regime. Okay, and so, for example, if I look to the support, I will explain in a minute. If I look to the support of this measure, it will give us somehow will somehow tell us where is the phase transition. If I look to the support of this measure, I look to the left, I mean to the minimum value of the support, so this will give us somehow where it is the point at which occurs the phase transition for the Erdős-Rényi random graph. So that's why we are saying that this model feels or detects the phase transition. Okay, so let me try to explain this. So again, so remember the limit of operation measure was something proportional to the expected time, mn of lambda. Now, mn of lambda denotes the expected time, the expected return time of the random walk on this graph here to the vertex 1. Okay. And what we can show, in fact, is that when n goes to infinity, this, and for any interval a, this converges to some measure here, p infinity of a, and we can actually characterize explicitly, let's say, the density of this measure, which is proportional to zeta lambda times some function which depends on lambda, okay? And this zeta lambda here is the survival probability of the branching process with offspring Poisson distribution of parameter lambda. Okay, we have, I mean, this is explicitly, but it's an ugly, a polynomial with respect to this guy here, so it's, I mean, we have it explicitly, but so I'm not telling here. And in particular, as you see here, so we know that when lambda is smaller or even equal to 1, this guy is 0. Okay, this guy is 0. So that's why the support somehow of this measure is concentrated at values larger, strictly larger than 1. So if that's what I was saying, if I look to the support, somehow it is telling me where is the parameter at which occurs the phase transition for the heterogeneous random graph. Okay. So there is no emergent dominance in this case, but at least we can characterize what is exactly the limit distribution. Okay. And just to conclude, let me just to show. So what you see here is just an example. We are plotting the graph of P infinity versus Pn. Okay. P infinity is just a limit, so it's given by this red curve, something like this. Okay. And the points are just we for each choice of parameters lambda, we simulated a heterogeneous random graph with that parameter divided by n when n is 1000. We did that several times, and we can estimate what should be the value of p n of that lambda. Okay, and the set of lambda was discrete, so between 0, let's say, and 2 in this set here, and the distance is 0.1 between each point. And here we take again mu uniform. Okay. So I think that's what I wanted to tell you, that in this case, unfortunately, we don't have this emergent dominance, but I think it's interesting, this result, because we can, for example, characterize explicitly the limited distribution of the occupation measure when the volume is very, very large. Okay, and to conclude, for example, where we wanted to go is, for example, to try to ask a few questions, including, for example, what we can say for more general random environments, like say, for example, we could consider this in the Bernoulli percolation graph, for example. What does look like what would be, for example, the limit distribution P infinity? Yeah, but just that the graph is more, you have an additional structure, right? It's like you Z2, and then the edge can be just that's what we meant by Bernoulli percolation. Yeah, Z2, yeah, sorry. And also with respect to the first two examples, we wanted to understand also what happens if the states, for example, are sampled in a Markovian way. So instead of choosing independently at each time it reaches the boundary, I do it in a Markovian way. What happens in this case? And also what happens if I reset not at the origin, but I do a reset in a different, I don't know, according to some random distribution. What does it change, for example, right? So this is the typical question that we wanted to investigate, and that's all. So thank you very much for the attention.
Questions? Well.
No, I comment. I think your result is much better than it was true, because so all of us it's wrong that lambda equal 1 is a critical point. This is wrong, just wrong. So More interesting.
I don't know. Maybe.
I'd be glad, because if you prove it was 1, it would be wrong.
Okay, we had to understand this, and I think I mean there's something that is not the main point of all this, is that if I, let's say, have a model for a random graph which has some where there exists some regime where you have supercritical and subcritical, etc., we could run this random walk model on this random graph to have an idea of where it is where the phase transition might occur, for example. And I don't know if this is really useful, but it could be another possibility, for example.
I think interesting the way you
Okay.
No, my question was exactly that. If you can estimate the critical value using
So yeah, I mean,
simulation.
the procedure will be, for example, we could consider this Pn for large n, and I would just look to the support of this measure, and at least here you see the blue points here will correspond to the possible values of Pn for each lambda here, Pn of lambda for the different values of n. And here, for example, I would say the support is here. So it's not 1, but it's not very far. So it could be a way of also to tell you where the phase transition may occur. For general graphs, I mean, this case, I mean, everybody somehow knew it already, but this could be useful in this case as well.
the previous slide is the neo formula. What?
Yeah, no, it's again, I mean, because so I'm just saying that the density, I'm forgetting this part, it's just a constant.
It's the neo theorem.
Yeah, the renewal theorem is somehow is to say that, yeah, this converges to this, but then to identify explicitly this, it's there is an extra work to do. Yeah, it's non-negative, and yeah, I mean, in the paper we have wrote it just because here I didn't want to bother with the exact expression, but we have it explicitly. This depends on the survival probability at a given power, etc., etc. But it's explicitly known in this case. Okay. Yeah, I hope there is no mistake. Okay.
There's some reason that for some lambda you stay always below and then always. What is that around?
I think this is again, Daniel would have a better answer for that. But I mean, to plot the red curve here, for example, you need to plot, for example, zeta of lambda. Here there are other terms which depend on the zeta of lambda, which in turn is not giving explicitly. We need to approximate this, and I think this approximation somehow it's giving this behavior, I would say, because there is a small error at each time. I think that's the reason.
I'm coming back to your head. When he is sleeping, it stay in A or in B.
Yeah, no, I mean, it's just a caricature. I mean, just
this probability is the state.
yeah, somehow it's that. I mean, at least in the example of my cat, that's why every time I look at my cat, he's sleeping, because it's all the time in A somehow. And maybe there are two states A, B, and C. That's why either sleeping or eating and licking itself, something like this. But and the point is it's not that we don't believe that there is no learning, something like this. It's just that it doesn't explain by itself the emergence of dominant behavior. That's the point. And again, I apologize for not being precise, Roberto, but this is related to metastability.
Possibility that your cat is just pretending.
Maybe, yeah, no, yeah.
When you arrive,
Yeah, maybe. No, then I cannot explain, but yeah, probably. Sorry? Not really. But yeah, not really. Yeah. Let's say it this way. Okay.
Marzio, non muoverti troppo, Marzio, non muoverti troppo. perché quando ti muovi la voce scompare. Cerca di stare davanti al microfono.
Anyway, so and then so we met so many times, and each time was very good, and I really liked it very much because it was a way to enrich me both from a scientific and from the point of view of friendship. So best wishes to Antonio.
Thank you very
And
much.
now I will think we collaborate about many different problems, from metastability to linguistic to disordered systems and information theory. But now I will be talking about something that we never discussed together. So something about the reasoning model. So as you see, I think you can see now
Yes, we can see.
my slides. So the first slide is the title. The reasoning model is long-range interaction. A study of typical configuration. And now it's blocked, and I cannot move down. I don't understand why. Okay. So the abstract is not necessary. Then this is a work in collaboration with Titti Merola and Pierre Picot on my side. This is the model. The model is, you can see, Hamiltonian, is an easy spin system in one dimension. And all the notation, I think, is standard. I don't have to make any comment. What is the problem? We want to study the big measure of this system and see how does it, what happens when lambda goes to infinity. This is a short story of what is already known about the model. Because this model is rich of many very interesting features. So they started discussing this model in the 60s, and Ruel, Dobrucci, Gallalotti, Miracoli, so they studied the case alpha less than 0. And this is, so to say, the trivial case, because the interaction decreases in a very fast way, and so the system is like the nearest neighbors, and it's already known that in one dimension there is no phase transition for this model, as already Landau showed me really simple. Then in '69, and then there was some people who was discussing what could happen when alpha is positive. So it means, if you look at the form of the interaction, when the interaction decreases more slowly. Thomson and Katz conjectured there was a phase transition already in the first 3 years of the 60s. And we have to wait until '69 to be able to prove the existence of a phase transition from this model when alpha is large. And this was Dyson. He was able to prove that when beta is very large, there are at least two different measures, a mu plus corresponding to the boundary condition class that gives a positive magnetization, and the symmetric case mu minus gives a negative. Then we have to wait 10 more years, more than 10 years, to be able to start to say something about the alpha equals 0 case. Alpha equals 0 means we have a potential that goes like 1 over r squared. In this case, Frey and Spencer, with a suitable definition of contours, were able to reproduce some sort of Piles argument, and so show that, again, for beta very large, there are at least two different measures, a mu plus and mu minus. In the second year, using these contours introduced by Frey and Spencer, Imbright is able to construct a fraction and prove some very good bounds for the two-point correlation function. This result allows a lot of people, Eisenman, Chase, Newman, and Imbri, to analyze in detail the peculiar properties of this model without frequency. In particular, what is known, well, already conjectured by physicists, so the Taurus effect. The Taurus effect is that the magnetization at the critical point is discontinuous. It's not zero, but it is a jump. Or the Taurus-Foster effect, which is about the existence of two different, below the critical point, there is another point where the phase is changing. And in particular, this is very particular, this model, the correlation function decreased with the potential, with the power that depends on the temperature. Okay, this was the main results about this model, and in particular, the last part is very, very important. It was unexpected and was proved in a very sophisticated way. In 2005, Ferrari, Naylor, Presutti, and myself, they introduced, inspired by the work of Frederick Spencer, a new way to describe the spin configuration in terms of triangles. This approach suggested a very natural way to describe the phenomenon of phase separation. In ferromagnetic systems with beta larger than beta c, we have two phases, the positive one with m equal m beta, and the negative one with m equal minus m. If we consider the system constrained to have m equal some small m that is smaller than m beta, we have the phase separation. One phase is attached to the boundary, and the other one is repulsed and form a droplet inside. In one dimension, we do expect to get something like this. This is the interval, it's one-dimensional volume, and you have a droplet of minus in the middle, and two regions with a plus outside. If you consider the measure U plus and U minus, and consider a convex combination of them, you can get an average value for the magnetization equals small m. But if you choose this, the coefficient of the convex combination is 1/2, 1 minus m over beta, you get the average is m. But the two measures that you are considering, U plus and U minus, are translation invariant. And so the linear combination cannot describe a spatial distribution, but that one with a droplet in the middle. XXVI in 1967, for the easy model with nearest neighbors in 2 dimensions, they were able to deal with this problem using the Gibbs measure, but conditioned to the canonical sum. So to say, this measure where Sm is just the set of configuration where the average magnetization is equal to small m. What XXVI were able to do was to prove in this set of configuration that the typical configuration, if I put a plus boundary condition, is just a large I of two positive spins with average and beta, a large C of positive C of average and beta, and an island with a minus sign. Then this was in 67. In 1988, Dobrushin, Kotesnik, and Schwarzman a big improvement in this result, rigorously deriving the phenomenological theory of Wolff that gives the exact shape of the spatial region occupied by the one phase in media. What we do is to study this phenomenon in the case of D1 for the long-range ferromagnetic interaction that I have already introduced. Obviously, the second part, the one given by Dobrushin, Kotestian, in this case is trivial because we have no space to describe the shape of the globe. Is just a segment in the equal one case. But we are able to study different things. For instance, if you consider the distribution, the Dobrushin boundary condition, so we have on my volume, I have a left side minus boundary condition and the plus boundary condition on the right. The system becomes in this way. There is a section with the average in the case of minus beta, and another one with plus minus beta. And there is the separation point. And so we did study the behavior of this separation point. Then in the second paper, we did the analog of what did Milos Sinai and proved the existence of this droplet, and we were able to show that the typical configuration has exactly of the form that the phase separation suggests. And then the third work that now is still in progress is about the localization of this. Because in the case, in the two-dimensional case, they were able to say the form of the droplet, deriving this Wolff construction, but they were not able to say anything about how it is disposed in the volume, in the general form. What we do in this case, because it's simpler, obviously, simpler, we are able to prove the laws of the localization of the droplet. Indeed, the probability distribution mu x, where x is the center. Okay, to prove these results, first some comment. In the case beta infinity, so to say for zero temperature, if I say beta infinity n equals small m, the ground state is the only available state, and so the ground state is just the description of this phenomenon. In what you get what you expect, but in this case not with a real plus spin fixed and minus spin fixed. What is important, that the ground state in this case is degenerate, because the interval of the minus sign can be everywhere in the volume. For beta less than 0, what happens is that this degeneration is removed. And what we are able to prove, and now we will discuss this result, is that for alpha larger than 0, just scaling the volume from minus L to L to minus 1 to 1, so working in a macroscopic space, the droplet is, we find the droplet is fixed in the origin. But for alpha equals 0, the distribution of the center of the droplet is given by a function f of x, symmetric with respect to. So this is not a very usual case. When you go from microscopic to macroscopic description of the system, in general, you don't get real form. With the scaling from minus L to minus 1 to 1, you don't get function. You just get the distribution, and just doing some scaling different, you can get the Gaussians or some other distribution. In this case, we get exact a function. that is symmetric with respect to the origin and is concave. What we will show now in the following is that for beta very large, when we are able to prove something, the basic mechanism behind our result is due to the elementary fluctuation produced by two consecutive spring flips. Okay, now I will start to go more into detail. So the Hamiltonian is of this form. The ground state is just a sequence of plus signs. A generic configuration now is what? Is just a sequence of intervals of different signs. And the board and the boundary points are the so-called spin flip. So I can call a spin flip the point E plus 1/2, where sigma I is different from sigma I plus 1. So to describe a configuration, instead of using the sigmas, I can use these spin flips. Once I have fixed the boundary condition, and I know the position of the spin flips, I can recover the configuration without any ambiguity. What we did to construct our contours is to group couples of spin flip starting with the closest one. So, for instance, this is a possible configuration on the first line. In the second line, I've drawn the red points. There are just the spin flips associated to this configuration. And then I start coupling the spin flips that are closest. And so there are these two. Then I ignore their presence and I consider the next couple of spin flip that is closest. And I get to the fourth line. And the first and the fifth line concludes this argument because the last two spin flip points are coupled. This procedure is possible to perform this procedure and get a complete correspondence between the sigmas, a configuration of states, and a collection of triangles. These are triangles. And it is possible to show that this relation is being checked. Knowing the sigma, I can construct the T, and knowing the T, I can reconstruct the sigma configuration.
Not exactly, because you don't know if it's plus or minus.
Pardon?
So you don't know. So you know the regions, but how do you know it's a plus
No,
or minus?
given the boundary condition,
Give us a boundary.
as I said before.
Okay.
No, just in the previous connection, always the boundary conditions are fixed.
Okay.
So if the boundary conditions are plus, then the sequence is plus, minus, plus, minus, plus, plus. If the boundary conditions are minus, the sequence is minus, plus, minus, for the same spin flips. So once I have given the boundary condition, the connection is not ambiguous.
Okay, thank you.
There are, when you do the construction explicitly, you can have some ambiguity, but it's always possible to give a prescription to avoid this ambiguity. So if I call capital T the set of compatible triangles, by compatible I mean a family of triangles for which it's possible to perform the connection between the triangles and the sigma. And so the partition function of my system, that is the sum of all the sigmas sigma lambda, can be written as the sum over the families of T contained in this T. What is the main feature of this description? First of all, we can call mass T the length of the base of a triangle. And what happens, and this is due to the way we construct the triangles, the distance between two triangles is always larger or equal to the inf of the mass of T. This is very useful, because if I consider now my Hamiltonian and consider, and I have a region made in this way, there is a triangle of length T, and the region without triangles of the same length, for arbitrary configuration outside this region, I can perform, but I can get very easily a bound with the difference between this situation and a situation where the triangle is. And this is what we get. For alpha larger than 0, we get C alpha to the alpha. And for alpha equal 0, the lower bound is a log of the base of the triangle. I am saying alpha larger than 0. I should say alpha between 0 and 1. The way that we did it in our work, actually the limit is not 1, it's smaller than 1. Log 3 divided by log 2 minus 1. But then there were improvements, so now it's possible to prove this result for alpha from 0 to 1. Okay, now with this result in mind, what we can do is the following. If we consider a generic set of triangles and order in the way that T1, T2, Tn is such that T1 is smaller than T2 is smaller than Tn, given the condition that the distance T prime is always larger or equal to inf of T and T prime, starting with the smallest one, I can use this inequality. And then I can, one by one, I can cancel all the triangles and get a lower bound of this kind. H of T is larger or equal than C sum I to N of Ti to the. Unfortunately, this result is not enough to get a sort of pilot sample, because I cannot just extract one single triangle and leave the other outside. I just to explore one particular region, I have to control almost everything. So we have to do something more to get a pilot system. And these are the way to define the contours that we did. Calling T1, T2, Tk gamma a family of triangles, the mass of this gamma is just the sum of the masses of the triangle decomposed. And this gamma with alpha is this quantity that will come out later. Now what is important, the distance of gamma and gamma prime is the inf of the distance between all the T that belongs to gamma and the T prime that belongs to gamma. Now to have two contours that are compatible, we define the distance between gamma and gamma prime should be bigger than C at the minimum of gamma cube and gamma prime cube. Gamma, I recall, is the mass of the set of. The reason that we put gamma cube is arbitrary. We made no effort to optimize it. Anyway, this is sufficient to do what we do. Now, as you already obtained the injection between the configuration sigma and the families of triangles T, now we have another injection between the family of triangles and the contours. The result is that a configuration of triangle can be described in terms of contours. It has a sequence of objects equilateral. And now this allows, if you express our Hamiltonian in terms of the complex gamma, and consider a configuration with set gamma plus a gamma 0, we can extract any gamma 0 because we control the fact the interaction between each of these groups is very good. An important crucial point now, since we have defined the contours are very complicated objects, and we have to control how many there are that are contained at a given point. And this is the main section of this paper about the definition of these contours. And it's possible to prove that the sum of all gammas that contain the origin and have total mass small m per e to the minus beta per gamma, I record this gamma is this quantity is the third line of this. This can be controlled. It is equal to 2 times e to the minus beta 2. This allows to get the pilot estimate and to perform to prove the convergence of the cluster expansion. The cluster expansion in this case is what? If we consider a set of configuration S of B, and I consider the partition function, this set of configuration, and call sigma zero the ground state. This ground state can be anything, as you will see there. But anyway, this set of configuration will have a minimum, and if these minimums don't degenerate, we have a single ground state. What happens in the cluster expansion is that the log of this partition function can be written as minus beta per the Hamiltonian evaluated in the graph state, plus a sum of activities of the sum of activities that I will explain what are, plus an exponentially negligible result. So, what is nice about the cluster expansion that we write the log of z back as an explicit form of the Hamiltonian of the ground state, plus the partition function of a gas of points connectivity C. These activities are very easy to evaluate because this is simply e to the minus beta, the difference between a single spin free, the energy of a state that is equal, the state that is the ground state with a single fluctuation. And this fluctuation is the fluctuation with two consecutive spin frames. And it is possible to explicitly evaluate. So this, the exponent here is something that is always possible to evaluate. It is the difference between the ground state, the elementary fluctuation of the ground state, and the energy of the state. Now, if you call capital P lambda the set of all families of compatible triangles, then you can define the set of all triangles that are small. The capital P small is the set of all triangles that are compatible, but every one of these triangles has a mass that is smaller than epsilon s times lambda, where epsilon s is something goes to 0, where per lambda goes to 3. So all the triangles in P small are not not proportional to lambda, but are smaller than lambda. this set is very important because if you consider now
excuse me, Marzio, I
the,
don't
the
understand.
cluster
Marzio,
expansion of the grand canonical ensemble,
Marzio,
from beta very large, what happens is that you are just left with this small triangle. And all the other triangles are negligible. So you can describe the plus phase with a large C of classes with the island of length 1 of the minuses, and these are put then the free. So you can describe this object as a free dust of particles that have these activities. And the minus is a large C of minus with this the fluctuation of dust. Now, if you define another subset of triangles, as the subset of triangles made with a T0 union T prime, where T0 is a macroscopic object of length rho lambda, and all the other triangles are small, then you have something that you can make a picture of this kind. So you have a large triangle, and then you can put everywhere, in a way compatible with the existence of these large triangles, or small triangles. This object is what now? This object describes the system that has the phase plus on the right, the phase right again on the left, and you will do a region with the phase minus. And this region has a length. Then you can consider also a subset of this, and this subset is all the members of the previous family where the big triangle has center in the point K. So this is the definition. So it's just a subset of the previous one. Once you have defined this kind of object, and we consider also the set of the canonical ensemble of the set of particles, or set of the configuration with the magnetization small m, we can consider three sets. The sets, the first one is the canonical ensemble. The second one is the set of spin configuration that when I transform them, I describe them with triangles, a big triangle with base of length and many small triangles around it, inside the big triangle and outside the big triangle. And then S lambda rho chi is a subset of this where the position of the big triangle is fixed. Now, this allows to write down three theorems. The first theorem is the measure of the S rho epsilon C epsilon 0. Epsilon C I will discuss later. So yeah, there is an epsilon C because I don't consider the triangle really of a fixed length rho, but can fluctuate a bit. This measures constraint to the set S and the grand canonical set tends to 1. What is the meaning of this theorem? I get this theorem for beta very large, and alpha strictly, and this is for alpha from 0 to 1. This means that the configuration of the typical configuration of the canonical ensemble are configuration exactly of the form that was obtained by XXVI from the two-dimensional space. We have a big droplet with the minus sign in a large C of plus sign, where the droplet is average minimization and beta, and the large C has minus beta, and the large C has minimization and beta. The second theorem is that instead of considering S of rho, we consider S of rho fixed. So we fix also the center of the big triangle. And this time, the measure is conditioned to all the configuration that have a big triangle of length rho. And so this describes the probability of having the triangle of center chi compared to all possible other cases. Now, what is important, this for alpha larger than 0 and beta very large, this measure for lambda that goes to infinity goes to 0. So, for any chi different from 0, so this is distribution. The measure describes something that is fixed in the origin. So the triangle, the big triangle, is to be fixed in the origin. And then the third theorem, and this is still in progress, and I will briefly discuss why. Going to consider the same measure for the case alpha equals 0, the limit is completely different. It is a function f of k, and this function is symmetric, concave, and positive. On the set -1 plus rho divided by 2 and 1/2 minus rho divided by 2. And in principle, I can even say how does it look like, this function. This function is possible, actually the function is not this one, the exponential is the probability. This function is morally the solution of this. And our work is still in progress because you have still to completely prove this result. What are the difficulties? The difficulties are that when I stated the theorem 1, I use this S rho epsilon C epsilon 0. And this is something more complicated because I have to prove the theorem 1 is not enough to consider a dark triangle of length rho. It's necessary to consider a triangle R of length above rho plus large triangle but smaller that are around it. So what is called what Miro XXVI called the facet zone. So the real capital thing that I should consider is this one. The definition is the union of the rho star such that rho star goes from rho minus 6 epsilon c to rho of sets of this sort. There is a T0 that is of length rho star. There is a set TE that are triangles that are external to T0 and are not small. And the sum of these, but the sum still then is not very big. The sum of this T that belongs to TA is rho minus rho star lambda, so is of the order epsilon c. And then the t prime, they are the standard that belongs to. And now, to consider all these terms is possible, and we are working on it. And if we consider only T0 and neglect of this term, this is the result of the quantification, e to the f of x. But if and now we are still working with this object, and we have to control this ratio and control the limit of this ratio. We already know that the limit exists, and we have to see what is the relevance of the contribution due to this thing. Okay. This is the end of my talk.
Can you
Just one comment. One reason that this result is interesting and non-trivial is just this last line, because it's not common in studying problems in microscopic, the limit macroscopic of the microscopic systems to get a function. Usually you get a distribution, and you get something that fluctuates. In this case, this quantity does not fluctuate, but is macroscopic, moves macroscopically in it. And I don't know of other cases where this happens.
Okay, Marcio, can you hear us?
No, I don't think so.
Come?
Okay, you can. Okay, so can you hear now? No? How it works?
I can hear it. Yes.
Okay, perfect. So now we will start with questions. Questions of the audience. About cluster expansion, Roberto.
Cluster expansion, finally. Someone
Yeah, I will use different cluster expansion for this moment, but I mean, it's been a very detailed work, more detailed than what I can do. That's all, my whole company. That's why he takes this function. He does a very detailed job of. I mean, I'm happy to see, Marcio, that you do a very detailed job in some different contributions to the cluster expansion, instead of just bounding away as much as you can. So that's why you get this function. So I hope you succeed in bounding the last term. That's all I can say. I mean, I'm not able to do such a detail, such a level of detail. Definitely.
No, I don't understand.
Can you hear?
I can hear, but no. I was not able to hear the words.
So.
Antonio, you speak louder. You speak louder. Can you repeat the question?
Max, you cannot expect me to ask you about cluster
Because I don't understand.
You should ask Roberto about cluster expansion, not me.
Do you hear me now?
Roberto,
You hear me
speak
now?
louder.
Roberto, o que ele está falando aqui? No robô. É que no robô.
I don't know.
Imagina. Imagina que é o robô.
Tem que falar no robô?
Marco, can you hear me?
Yes, I can hear.
Okay.
What is it?
So no, I'm impressed because you do a very detailed summation of your cluster expansion. I am unable to do such details. That's why I'm commenting here, people, that you do more details than what usually a person working in cluster expansion would do. Many things will be bounded away, this conversion, that's it, goes away. But you are really trying to obtain a complete expression out of it. So this is very nice, and I hope.
I mean, you mean, let me go there. When the way to define the cluster expansion per a subset of configuration.
Yeah, and the way you sum it, yes.
Yes.
You have to do a very detailed consideration, different
This
cases.
one. You are talking about this one.
Yes, I'm talking about that.
Okay.
Because typically,
And so this I was not able to go into detail, but what is important is that when I introduce, because I consider them Hamiltonian, I subtract the energy of the ground state, and then I can define the activity as a very object that reflects the structure of the ground state.
but I
Because
mean,
in fact, I call, when I write, this is a C of X. Usually the cluster expansion, this first term does not depend on X.
yes.
And in this case, if you do this cluster expansion explicitly, and you are considering the fluctuation with respect to the given ground state, that is not the standard ground state. And so the activity comes out in this form, that the way that I see beta of X that I have. Now this is 1, 2, 3, 4, 5. The sixth line in this slide. The exponent is something that depends on, because depending on which is the point where you are, the interaction with the ground state is different.
Yeah.
Because in the standard cluster expansion, the way that I wrote it, okay, is this the problem?
No, that's the thing. I mean, you do something more detailed treatment of the standard cluster expansion approach. That's what I'm impressed.
He's
Now-
happy because you do better than he
No,
usually
no.
does.
Yeah, you do better than what I would manage to do with this. Yes. So
But the way that I do the cluster expansion, apart from this explicit story, is that the stand. I have my system of contours that are weakly interact. So I can construct polymers in the standard way. So each interaction of two polymers, I can write ±1, and then I can write the polymer. Then I have to describe the activity of each polymer and control the convergence of the sequence. And this is what we did in the first of this paper that I quoted. In the paper of 2000, no, it's 14, in 2014.
okay.
So your question is that you don't.
I don't have a question.
How did I do?
Question, but if you want, I can ask a question. So, in this long-range model, so you obtain a cluster expansion whether the polymers are hardcore or you put them interacting through the long-range terms.
No, my starting point is a partition function. The Hamiltonian is in terms of this contours plus the interaction with it. I write my Hamiltonian as the sum of Hamiltonians of the single contour plus the interaction with it. And the term of interaction is just a complicated object, but the philosophy is the philosophy of the usual cluster expansion, the expansion with beta close to zero. For an interacting system, for beta very small, what you do? You consider the one point pocket, and then you have e to the sigma I, sigma j, and then you write +1 -1, so this allows you to construct polymers.
Okay, and these polymers are hardcore, so they have.
And these polymers are
Because for some long range you can do it with polymers that interact, that have a two-body interaction.
No. I construct polymers to have objects that don't interact.
Okay, very good. That was the question. Very good. I would have done the same. At this point, we are at the same stage. But then I think you do much more detail than what I would have the patience to do. Okay, thanks, Marcin.
Okay,
Okay.
is there any other question? No. Okay, so let's thank Marcio once again.
Ciao allora.
Ciao, grazie.
Ciao.
Hai ricevuto da fotografie che ti ho spedito ieri? Tu hai ricevuto?
Le fotografie che ho ricevuto.
E non l'ha
Le mie fotografie
nemmeno
che ho
ringraziata.
ricevuto.
È stata presa 20 anni fa. Denise l'aveva. Ciao Marco.
Ciao, grazie mille. Ciao.